Today's AI networks are hitting a wall. They are hungry for massive bandwidth and incredible speed. But traditional optical connections cannot keep up because they use too much power and add too much delay. This is where linear pluggable optics over LPO comes in, a new approach that simplifies the optics by removing key power-hungry chip and pushing that work to the main computer. In this work, we'll uncover what LPO is, why it's a perfect fit for AI, and how it delivers the power savings and speed we desperately need. But to understand why LPO is so crucial, we first need to look at the powerful trends forcing the change. Modern AI data centers are facing a perfect storm. Bandwidth is exploding with 800 gig links today and 1.6 tera on the horizon. And that surge creates two huge problems: power and latency. The traditional fix, a DSP chip inside every optical module, has become the bottleneck because it's power hungry, runs hot, and adds nanosecond of delay. That hurts AI synchronization. LPO answers this by making a radical simplification. It removes the DSP entirely to cut watts and shave latency. So what does an optical module look like when you remove its brain? Let's take a closer look. LPO is essentially a dumb optical module in the best sense, where a traditional module has a smart DSP to clean up signals, and the LPO module doesn't. It keeps only the essential to convert electricity to light and back. All the complex smart signal connection, equation, and timing move out of the module and into the host ASIC. So the module becomes a simple, ultra-efficient converter that pass the painful signals through. This fundamental architectural shift leads to some dramatic difference. Let's compare them head-to-head. The differences are stark. Without DSP, LPO module typically use 30 to 50% less power and have nearly zero added latency because the signal passes straight through. The trade-off is that capacity moves to the host, which now must be much smarter electricity. And while the DSP module excels at longer 30 links, LPO purpose-built for short, fast, clean links inside a rack or row. The key takeaway is that LPO trades module capacity for huge gains in power and speed, where AI needs them for most. So, what does this smarter host actually need to do? Let's start with the transmitter's new responsibility. With no in-module DSP to clean up the waveform, the host transmitter has to ship a greater signal from the start. It must precondition and shape the painful output with proper FFE, stay highly linear so the optics are not driven into distortion, and keep timing rock solid because any jitter runs straight onto the light. In short, the host TX now does the DSP's job before the bigs even leave the chip. Of course, it's two-way street. The host receiver has an equally tough job on the other hand. The host receiver sees the raw optical signals convert back to electrical without retiming. So it needs strong analog equalization CTOE to restore high frequency detail, powerful digital equalization like DFE to cancel inter-symbol interference, robust CDR to look onto a shaker input, and host side flag to clean up remaining errors. Modern SerDes are being designed precisely with this capability to handle LPO's demands reliably. That's a lot of engineering. So what's the payoff for AI? For AI, LPO delivers what matters: massive power saving at a module that scales to low rack energy and cooling, ultra-low latency that keeps thousands of GPU tightly in sync, and simpler optics that can reduce the cost and raise port density so we can pack more bandwidth into a switch, directly attacking the core bottlenecks in AI scaling. Such a fundamental shift does more with a trade-off. So it's important to understand LPO's limitations. LPO isn't universal. The sweet spot is a short reach, typically in rack or rack to row, rather than long haul links. It also creates host dependency because it only works with the newer SerDes design for linear operation, and it demands tighter integration and more testing between switch and optical vendors to ensure everything is tuned and interoperable. These are not deal breakers. They are design constraints. Here's how to deploy LPO successfully. Use LPO where it shines. Show clean links inside AI clusters. Verify your switch or NIC silicon is especially LPO ready when strong CTOE DFE and linear modes. Co-test host and optics in the lab and work closely with the vendors. And link on link trainings, CMIS terminally, and evolving standards so multiple vendor deployments run smoothly in production. Let's bring it all together. Why does LPO matter for future of AI? Here are the summarized images showing you why LPO is a smart, necessary trade-off. By moving processing out of the module and into a capable host, it tackles the twin demand of power and latency head-on. It does require more advanced SerDes and careful system validation, but the reward is a cooler, faster, more efficient network for the short critical links that power AI cluster, and immediately critical step that helps our infrastructure finally keep pace with AI's demand. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share comment down below. Lastly, please share the video with the people who may be benefiting.